Okay, guys, so implicit differentiation, I'll do this over 2 days. First day, we'll do first derivative and hopefully tangent line. If not, then we'll do tangent line tomorrow. We have a brief quiz tomorrow, but it won't take the whole period. It's a timed quiz, so you get 25 minutes. Whatever I don't finish today, we'll finish tomorrow. Okay, so I just borrowed this straight out of the book, but they have this graph of this relation x cubed plus y cubed minus 9xy equals 0. And you'll notice that y is not isolated, right? Y is not isolated. So what I did was I went on the computer, I went on Wolfram Alpha, and I told Wolfram Alpha to isolate y. Would you guys like to see what I got?
Yes.
It's pretty cool. You ready? All right, here we go. This is what Wolfram Alpha came up with. 3 different solutions when it tried to isolate y. And I'll try to read it to you. It's a little hard to read. It's not that easy to read here. Let's see. I'm reading the first one. It says y equals 3 times the cube root of 2x all over the cube root of the quantity square root of x to the 6th minus 108x cubed all minus x cubed, but still inside the cube root, plus the cube root of, and then the square root of x to the 6th minus 108x cubed minus x cubed all over the cube root of 2. And then Wolfram Alpha was kind enough to try to help me find the cube root of 2 and such, and went ahead and gave me an approximation version of the same exact thing. So that's an approximation. What a mess. What a mess. And let's go back and look at this graph. Or let's go look at the graph. This is the graph of the function. Pretty nifty. It has a loop-de-doo. The scientific name for this, the mathematical name for this is a loop-de-doo. The writer can correct my spelling. Is it correct? Pretty sure that it's called loop-de-doo in math. No, I'm just kidding. But what's the first thing you notice about this graph? It's not a what? It's not a function. Well, no wonder it was so hard to isolate y. Okay, so the formula was, or the equation was this. It's hard to isolate y because, well, first of all, it's not a function. And so you also have the whole issue of how do you isolate a cube variable, you know, like how do you do that? Well, there is a formula called the cubic formula. You guys remember the quadratic formula? X equals negative b plus or minus radical. You know what I'm talking about? Yeah, there's a cubic version of it. It's a little bit longer. The song is a little longer, quite a bit longer. And that's, I think, how Wolfram Alpha was able to isolate y. But what a mess, right? Okay, so why were there 3 answers? Well, it could have something to do with the fact that this is not a function, but it's made up of parts that are functions. For example, this piece here in blue is a function, right? And this piece is a function. Both those pieces on their own do pass the vertical line test. And this piece in purple passes the vertical line test. So it's like 3 functions maybe kind of glued together. But what's most important about this graph that I noticed was it's differentiable practically everywhere. You guys remember what that means? Can someone remind us what that means? What does it mean for a graph to be differentiable? Differentiable. No sharp turns. Yeah, there's no sharp turns on this thing. Right? There's a couple spots on the graph where we might not be able to find a slope, but almost everywhere we have tangent lines with well-defined slopes. There's one right there, right? Up here we have a horizontal tangent. We'll find that tomorrow. We've got a tangent line right here, right? There's tangent lines out here on the left. Right? Move that over. You guys see what I'm doing? I'm saying that this graph has a derivative practically everywhere. There's a slope. The only spots I noticed where it wouldn't have a slope, at least from a visual first glance, is I don't think there's a slope right here, because that's vertical. I can draw the tangent line, but the slope is undefined. Same thing happens at the origin. See what's going on? So almost everywhere I have a slope line, and there is a slope. But if I can't isolate y, how in the world am I ever going to find the derivative to find those slopes? That's a real problem. I guess I could isolate y and then try to take the derivative of that thing. Yuck. There has to be a better way. Right? Okay, so how do we take the derivative of such relationships so as to find the slopes at various points? If there are slopes, we should be able to find them. Right? Okay, so the process is called implicit differentiation. And the process of implicit differentiation allows us to find the derivative of a relation or function even if y is not explicitly given. So if y is not explicitly stated, if it doesn't say y equals, blah, 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 and y is not isolated, we can still find the derivative using implicit differentiation, which is the topic of the day. So first thing I did was I showed you the need for a new method. I said there's some functions or relations that are too hard to take the derivative of if we have to isolate y. So mother's, what do they say? Necessity is the mother of invention, right? So if we have a need, we invent a method. Okay, so implicit differentiation, it's really just the chain rule, but it works on problems where y is not isolated. We'll come back to this problem later, but we'll do it tomorrow. But I'd like to just show you how to do implicit differentiation again in case you don't remember. Okay, so it's a four-stage process. Okay, first we differentiate both sides of the equation with respect to x. And don't forget the chain rule. Then we will collect all terms that contain y prime on one side and all others on the other side. Then we will factor out the y prime and divide to isolate y prime. Okay, so you can think of it this way: differentiate, group, factor, divide. That's how it goes. Differentiate, group, factor, divide. By the way, differentiate is the verb for take the derivative. Okay, because you didn't know that word. Okay, so on some of the examples, you don't need all four steps. You can just do like the first two and then skip straight to the fourth. But on a really complicated problem, these would be four steps you'd have to follow very carefully. So we will come back to that ugliness problem that I had up a minute ago. We'll come back to that tomorrow, but for now, let's just practice some really simple ones. Okay, can I move the slide? Okay. So we're going to find dy dx for the curve y squared equals x. Okay, now that would not be hard to isolate y here. You could square both sides. But I'd like to do my new method. I don't want to isolate variables. That's no fun. Let's jump right into the calculus. Okay, so step one said to find the derivative. So find the derivative of both sides. Okay, so what I'm doing is I'm taking the equation, I'm putting a ddx on both sides like this. Or if you want, you can take your y squared equals x and put a prime on both sides like that. Doesn't matter. Write it either way. Okay, what is the derivative of y squared? Well, we need the chain rule, right? Remember we said when the independent variable differs from the variable in your expression, you need the chain rule, right? So what would be the derivative of x squared? 2x. But what's the derivative of y squared with respect to x? It's not 2y, it's 2y times the derivative of the inside being y. If I take the derivative of x squared, we all know it's 2x, but if I take the derivative of y squared, it's going to be 2y times the derivative of y. That's the chain rule in effect. You have to follow the chain rule. Okay, so I'm just going to make a little note at the top of the board here. If you're doing d dx of f of y, you have to do f prime of y times dy dx. It's the chain rule. Very, very important. Okay, so what did you guys say when I first said what's the derivative of y squared? Some of you said what? 2y. You were right, you just need a dy dx also, okay? So next time don't say 2y, say 2y dy dx. Okay? Let's go to the right side of the equation. What's the derivative of x? That truly is 1. Yes. Okay? Step 2 is, what we're supposed to do is basically group any terms that have dy dx on one side, or y prime you could say, and then anything that doesn't on the other side. Well, that's already kind of done for us, right? So we don't really need step 2 for this problem. It's already separated. One term on the left, one term on the right. The one on the left has dy dx, the one on the right doesn't. Okay, then the next step was to factor out the dy dx, but that's already done too. So we can skip step 3. We don't need steps 2 and 3 for this problem. It's time to divide. The answer is dy dx equals 1 over 2y. And that's the answer. Okay, so I just did my work in Leibniz notation because that's what Mr. Lynch did last year. Now I'm going to do it with Lagrange notation. So I'm going to redo the exact same problem. Your work would look like this. Do a prime on both sides. The left side is 2y times y prime. The right side is 1. And dividing, we get y prime equals 1 over 2y. I think, personally, I like the second solution better. I don't like writing dy dx. It's a little harder on the eyes. I would rather just write y prime. Just remember, by y prime we mean dy dx and not dy d something else. Okay. You can pick whichever method you want when you're doing your homework. So step 4 was where we divided. So we really only need steps 1 and 4 on this problem. Okay, let's go to number 2, example 2. This one's asking for the first derivative and the second derivative of this circle at 3, 4. Okay, so first let me try to help you understand what it is we're accomplishing. So we're talking about a circle. What's its radius? 5, right? We're talking about the point 3, 4, so that's right. 3 up 4. It's this point right here. And effectively, the first thing we're trying to do is just find the equation, or not the equation, but the slope of this line. This tangent line. Okay? That most certainly has a slope. So we should be able to find it. All right, so let's just go through our implicit differentiation. I'll let you guys decide. Do you want me to use the dy dx or do you want me to use the y prime? Y prime. Okay. So I need to ask, what is the derivative of x squared? What is the derivative of y squared? And what is the derivative of 25? That's what I need to do. Okay, so what's the derivative of x squared? 2x, right? Careful here. What's the derivative of y squared? I told you what to say. 2y prime. Can't say 2y. And what's the derivative of 25? 0, right? I think we should move the 2x to the right side. And divide by 2y. It's like y prime is a variable and we're trying to isolate it. That's what's going on. Okay, so the answer is y prime equals negative x over y. Now remember, we were at the point 3, 4. So now it's time to plug in the 3 and the 4. So at 3, 4, y prime is negative 3/4. Right? Okay, let me convince you that you could have done that problem without the help of calculus. Look, this should have shown up on the, I'll bet this showed up on the SAT one year. Okay, this is the point 3, 4, right? Which means that to get to that point, you have to go over 3 and up 4. What's the slope of this hypotenuse? No, the slope of the hypotenuse. 4/3. If the tangent line is perpendicular to the radius, doesn't that mean that the slope of this is negative 3/4? Okay, so do we need calculus to solve this problem? Not at all. But we would never be able to answer the second question. The second question says find the second derivative. Okay, so we did need to do this. Let's take a look at the second derivative. So what does it mean to find d squared y dx squared? Now find d squared y dx squared at 3, 4. Well, we know what the at 3, 4 means. It means whenever we're done, we're going to plug in 3 and 4. Okay, but we're not done. So remember what this means. This means to find the derivative of the derivative. And that means we're going to have to go find dy prime dx. In other words, whatever we got in the first derivative, we're going to have to take the derivative again. Okay, so remember the derivative that we got back in part A was negative x over y. How do you find the derivative of a fraction? Using the quotient rule, right? Okay, so let's find the derivative. The derivative is going to be a quotient rule. This is like your u and your v. Okay, so we'll let u be negative x and v is our y down there. So we do low d high, so vu prime. Vu prime looks like this. Y times negative 1 minus high d low, that's u dv, or I should say u v prime. So that's going to be negative x there and y prime here, all over y squared. Okay, so we actually already got the answer. This is it. It's negative y plus xy prime all over y squared. I don't need two squares down here. So it's just over y squared. Okay, notice that your answer has 3 variables in it. X and y and y prime. I think it would be nice if we substituted in negative x over y for the y prime. That way it's 2 variables. Remember, we got that back in part A. This is our first derivative. And then we can kind of clean that up, you know. So here's the answer. Second derivative is negative y squared minus x squared all over y cubed. Okay, so what is the second derivative at 3, 4? By the way, this is how we write that. Second derivative at 3, 4 would be negative 16 minus 9 all over 64. So the answer is negative 25 64ths. Okay, so first thing I did was I used implicit differentiation. I got a derivative, and then I took the derivative of that. Okay, so I'm going to circle all my answers. I've got my second derivative here, and I've got second derivative with 3 and 4 plugged in. And then I'm going to go back up and circle my first derivative was right here. And then you can see my first derivative with the 3 and 4 plugged in. So I'll put stars by my answers. Okay, question? So negative x over y is the first derivative, negative 3/4 is the slope. Negative y squared minus x squared over y cubed is my second derivative. Negative 25 over 64. What does that number even mean? That is the instantaneous rate at which this slope is changing in this vicinity of the circle. So that's a little hard to understand, but that is called the concavity of the curve there. So we'll talk more about that in chapter 4. But this is just a ton of substituting. It's kind of a hard example, isn't it? Okay, this is number 20 from the homework, and I figured since you guys are going to be doing number 23 and 21, I'm sorry, actually this will probably show up on tomorrow, now that I'm looking at it. Let me go ahead and do this example, because although it's part of tomorrow night's homework, tomorrow we have a quiz, and we don't want to spend too much of the class time doing lecture, so let me just do one more example for you. It says first find dy dx, and then second it says find the equations of the lines that are tangent normal to the curve at negative 2, 1. Okay, so the first part is just implicit differentiation. Okay, so we'll call this parts A and B. Okay, so for part A, just ask yourself, what is the derivative of everything that I see here? Okay, so what is the derivative of y squared? Yeah, we said we're going to say 2y prime, right? What's the derivative of negative 2x? Negative 2. What's the derivative of negative 4y? Negative 4y prime. What's the derivative of negative 1? Negative 1. What's the derivative of negative 1? 0. And what's the derivative of 0 on the right? 0, right? Okay, so you have to do the whole equation, left side and right side. Notice there is one term in the middle that does not have a y prime. Let's move him to the other side. So we get 2y prime minus 4y prime is equal to 2. You can factor out a y prime or a 2y prime, your choice. And divide. So y prime is 2 over 2y minus 4, or you can think of that as just 1 over y minus 2 if you divide by 2 top and bottom. Okay, let's talk about part B. So what is it that we have? Well, the answer that we just found is able to give us slopes on the graph. And the original function that they gave us, although it's not really a function, it's more of an expression, like a relation, that can give you any positions. Well, they're talking about the point negative 2, 1. And they want the tangent line So if I'm not mistaken, I think my answer is going to look something like this. Y equals, and then it's going to be f prime of a, right? In this case, a is clearly -2. You can see right here that the x value for this problem is -2. So it's f prime of -2 times x plus 2 plus 1. Okay? This is f prime of a. This is x minus a, right? This is f of a. Interesting thing about this problem is they gave us f of a. It was 1. It says right here, -2, 1. So we got that for free. So this is actually going to be really easy. We're just going to plug we're going to find the derivative at x equals -2. So this is the only part that's kind of hard to figure out. What is that? Well, it's supposed to be found using your answer for part A, right? So if x is -2, y is 1, which means that the slope is going to be right in front of this x plus 2. It's going to be 1 over, and then what am I going to put here? I can't put -2. Notice that the function here requires me to plug in y, see? I circled in red at the bottom. I'm supposed to do 1 over y minus 2 to get the slope. Y is the y is 1, see? Be really careful here. So this is 1 minus 2. That slope requires me to plug in 1. Interesting. So you can see your derivative there is explicitly written with y's in it. So be very careful there. But the answer is simply y equals -1 x plus 2 plus 1 for the tangent line. And for the normal line, opposite reciprocal is +1. And there you have it. Circle our answers. Tangent line, normal line. Yes?
Can you explain how you got 1 over 1 minus 2 again?
Yeah, look down in the lower left, that's our derivative,
Yeah.
right? That derivative requires me to plug in the y value, not the x, see it?
Yeah.
Okay, back up at the top of the board, we have the point -2, 1.
Oh, okay.
So that 1 is what we're going to substitute in there to get the slope on our little point slope form. So you have to be really careful to plug in the right things in the right spots. Okay, and then we'll come back to this graph tomorrow. Our goal will be to find the horizontal and vertical tangents. I'm pretty sure that the origin has both a horizontal tangent and a vertical tangent, which is interesting because the curve self-intersects. So you have one of each. And then I think there's another horizontal tangent up here, wouldn't you say? And another vertical tangent right here. So we're going to find those 4 points tomorrow. It's a fairly challenging thing to do, but it'll be worth it. And if you want to see graphs like these, your calculator cannot graph these. So you can use this software, WinPlot. Have I shown you guys WinPlot at all? Okay, WinPlot, you can download WinPlot right off of the internet. Just do a search for WinPlot. It's the first link. Okay? First search result. And then you can enter in, this is really cool, you can actually type functions without the y isolated. Watch this. You can do x cubed plus y cubed minus 9xy equals 0. I typed 4 y's by accident. There is your graph. See? Your calculator can't do that. You have to isolate y to type anything into that calculator. And that just isn't feasible sometimes. So it is nice to have a software to do this. You'll notice there is a little gap in the graph there. The graph is struggling. The computer's trying really hard to graph that spot, but as soon as I zoomed out, it lost it. So sometimes you have to tell the calculator to redraw it. I usually just change the pen width, which makes it thicker or thinner, and then I'll try again. Still having trouble. Maybe I can get it to graph here. Let me change it to 5. Yeah, it's having trouble. Let me change this to a 0.1, and then change it back to a 0. There we go. have to appreciate what the computer is doing. It's not plugging in an x and calculating y. It's coming up with xy pairs that make this equation true. That's a different algorithm for their software. I mean, that's a really complicated loop. It has to pick an x and calculate the y's that work, and then it has to find another one. So it's having trouble plotting. And these can easily crash your computer if you zoom in and out too fast and stuff. So WinPlot can really calculate fast. Okay, so there it is, the loop-de-doo graph. We'll talk more about it tomorrow.